And now for the last part of the last problem. Let me clean up my screen here a little bit. Show that the series is convergent but not absolutely convergent. Well, let's remember what convergent and absolutely convergent. Absolutely convergent means it's going to converge when it's positive or negative. Convergent just means it converges as it is. All right, let's just examine it as it is. As it is, we have an alternating series because we have -1 to the r power over r ln r. The series goes from r equals 2 to infinity. Now for an alternating series to converge, remember the terms have to be getting smaller and smaller and smaller, and they also must be approaching 0. Well, if you think about this, in the denominator, r times ln r, both r and ln r are getting larger and larger and larger. Therefore, the limit as r goes to infinity of -1 to the r over r ln r is equal to 0. Therefore, it converges. Okay, so the original series as written converges. Now to check for absolute convergence, we're going to consider what if this were positive instead of negative. So 1 to the r over r ln r. And r goes from 2 to infinity still. Now what we have to do is think about this. Well, we know from the first part of this problem that improper integral converged only when k was greater than 1. Well, this is the same as the part A problem. And the power on the ln x, or in this case ln r, is 1. So in other words, k is equal to 1. And from part A, we know when k is greater than 1, it converged. Therefore, when k equals 1, it does not converge. Now, we don't have to go through all the explanation because we showed that in part A, that only converged, that integral only converged when k was greater than 1. So this does not converge, we can say, by the integral test. So part B, that series is convergent when it's written as it is, but it's not absolutely convergent because it's not convergent when it's negative and positive both. The end.